So yes, I'm Jolien. I'm working at the Institute of Astronomy at KU Leuven in the team of Leen de Sien, but I'm also closely collaborating with Lionel Sis, who is at the ULB. And today I'm going to talk about how a companion or multiple companions can shape the wind of AGB stars and how we can model them with phantom, of course. So thanks to Thaisa, you already know some things about this, but I'm going to repeat a little bit. So AGB stars are low to intermediate mass stars that have evolved towards the AGB phase. This means they have become red giants and they shed their outer layers through stellar winds, which have velocities up to about 5 to 30 km per second and mass rates of 10 to the minus 8 to 10 to the minus 5 solar masses per year. So again, as Thijs already explained a bit, for decades these outflows were modeled using a 1D approach because they assumed that these outflows were spherically symmetric. But the successors of these AGB stars are post-AGB stars and planetary nebula, which are known to have very complex outflows with a lot of intricate structures. So there is kind of a problem here, how we go from the spherical AGB stars to these complex outflows. So to understand these post-AGB stars and planetary nebula better, we should also study the outflows of these AGB stars better. And this is also what we're doing with the Atomium Large project, where we have ALMA observations of a sample of 14 AGB stars. So you can see them here, the same ones as Thaisa showed before. And you can see that indeed these outflows are not spherically symmetric. All of these outflows harbor complexities such as spirals, arcs, bipolarity, and some we also see disks. And by now it is believed that the primary cause of these complexities is the interaction of the wind with one or multiple stellar or planetary companions that are actually hidden in the wind. This hypothesis is also supported by population synthesis that states that about 50% of these solar mass type-like stars should be in a binary. And then we also have some observations, as you saw by Thaisa before, where we see some indirect signs that there is a companion shaping these outflows. And then we also have our simulations. So the awareness that there is a companion or multiple companions shaping these winds and that the wind is not spherically symmetric gives us some challenges and opportunities that we should try to solve. So at first, it tells us that we should be very careful with these 1D assumptions because they may give us incorrect results. So for example, the prescriptions that we have for AGB mass rates and that we use in stellar evolutionary models may actually be wrong, as we don't calculate in the impact of the companion and this distribution that is not spherically symmetric in the wind. So secondly, this also gives us the opportunity to bridge the gap with post-AGB stars and planetary nebula. So at first, one big goal is that we actually want to understand the orbital evolution of these binary systems. As in, for example, post-AGB stars, we see that there are many highly eccentric binaries, and we don't understand how these orbits get there, how they are formed. And then we also want to understand how the complex structures arise in these post-AGB stars and planetary nebula. So for example, here you see the typical structure of a binary post-AGB star, where there is this circumbinary disk, and there's an accretion disk around the companion, and jets are launched from it. And then here you see some examples of binary planetary nebula outflows. And you see they are indeed very complex, but they also resemble already a bit the outflows that we see in these AGB stars. So this is again an indication that both may be shaped by the same mechanism, being binary stars, and that by studying these AGB outflows, we may also learn something about these planetary nebula. And then the last thing here is what we are actually doing. So with all these novel images that we get from the ALMA telescope, this also gives us opportunities to really study these AGB outflows. And we want to do this by using both the observations and combining this with hydro models. So here you see an overview of my most closely collaborators. So here on the left, you see that we have some observational people, mostly within the Atomium Large program. But then on the other side, you see that there are many more theoretical modeling people. And our goal is really to work together to be able to combine our expertise on the hydro models with our expertise on these observations to learn more about what is happening in these AGB systems. So throughout the talk, I will go through the different parts of the slides to give you an overview of what we're doing. And I'm going to start with the AGB wind model. So this AGB wind model is developed by Lionel together with Daniel. And we are using that model now to study what the impact is of a companion on the wind of AGB stars. So in short, so we're using the phantom, and our AGB star and companion star are just represented by gravity-only sync particles. And then there is an SPH wind launched from the surface of the AGB sync particle. In the models I'm going to show, this is just a gas SPH wind. In this wind, of the models that have been published, cooling is regulated by an equation of state of an ideal gas with a polytropic index of 1.2. And then in the current models that we're working on, some H1 cooling has already been implemented. But as I said before, on Wednesday, Lionel is going to give a talk about this model and about the current developments that they are working on. But to give you already a sneak peek of what they're doing, they are working on a more accurate wind launching. So instead of this free wind, we want to get a more accurate physics there. So for example, Mats Esselders already worked on using a ray tracer to better estimate the radiation force and dust temperature, so to get a better wind launching. And then Lionel also implemented some dust nucleation already. And then in the future, it would be nice if we could implement the pulsations of the AGB star, since these are also important in launching the wind and in seeing which structures are forming. And then there's also more accurate cooling and heating going on. Okay, so now I'm going to show you some of the results we already obtained with these hydro models. So in previous work, Silke Maas and myself, we explored a certain parameter space. So we made different simulations in which we varied the orbital separation, the wind velocity of the AGB star, the companion mass, and the orbital eccentricity. And then by studying these different models, we came to two different papers. So in one paper, we focused more on the eccentric systems, and then we studied in detail how different wind structures form around the star, so close to the companion, and how this can result in various morphologies. And then in the other paper, we focused more on the impact of the companion on the wind dynamics, so on the terminal wind velocity, for example. And we studied if there is a parameter, a morphology classification parameter, that can tell us, if we just have orbital parameters, how complex the outflow will be. So to give you a bit of an idea of what is happening, if we have a companion impacting the wind, this companion has two main ways in which it has an impact. So at first, it induces the orbital motion of both stars around the center of mass. And then as the AGB star is orbiting around the center of mass and it's launching its wind particles, it already tends to create this spiral structure in the wind. And then secondly, you have also the companion that is orbiting, and this companion is also gravitationally attracting the wind particles. And in this way, it also tends to create a spiral structure. So then, in general, the impact of the companion will be strongest if its mass is large, the orbital separation is small, if the wind velocity of the AGB star is low, and if the eccentricity is high, then we expect complex things to occur. And these parameters are nicely combined in the following classification parameter that we studied in the paper by Maas et al. And we found that if this epsilon, this classification parameter, is high, then the impact of the companion will be rather limited, whereas if it's low, and if it's high, then we expect that the impact of the companion will be very strong and we get complex structures in the winds. So I'm going to show you some examples now. In these examples, we have a binary AGB system with a companion at an orbital separation of 6 astronomical units, and it's a solar mass companion. And then we're going to vary the orbital eccentricity and the wind velocity of the AGB star. So in most plots I'm going to show, you're going to see the orbital plane view. So we always take slices, so 2D slices of the 3D model, and show the density distribution. So this is the view you'll see most often. So for example here, so you see two different models. So it's almost the same model, but we varied the wind velocity of the AGB star. And the typical thing you see in these orbital plane slices is that we get a nice approximate Archimedes spiral structure. If we turn around the slices, so we look at it edge on, then you see that these two models are actually not the same. It's not just the Archimedes spiral. For example, in this one, you see that there's concentric banana-shaped arcs. I hope you can see it well. And then in the other one, you have bicentric, more elongated rings. So it's an elongation. It's like the model is flattened a bit, and it is due to the orbital motion of the stars. So then we come back to the orbital plane, and we're going to take a look at what the difference is between these two models. So we do this by zooming in to the structures closer to the stars. And then in the first one, we see that there is a two-edged spiral structure attached to the companion. But in the second one, there is actually a bow-shock spiral that originates in front of the companion. And then this bow-shock spiral also becomes a two-edged spiral, such that the global morphology in the orbital plane looks quite similar. It's 2 times the Archimedes spiral structure, but close to the companion, something else is happening. If we zoom in a bit closer, we see on this side again this two-edged spiral, on the other side the bow-shock, and now you can also see that there is an accretion disk forming around this companion. So this is a high density region around this companion, and if you take a closer look at this accretion disk, you can also see the velocity vectors plot on top of it, and then we see that actually within this accretion disks, material is spiraling in towards the companion where it can be accreted by the sink particle. And if you look at the edge-on view, you see that this disk has a flared shape. So these are recent new results that still have to be published, and we got this because of the inclusion of this H1 cooling, which we did not have in our first papers. So then we also studied what happens in eccentric systems, so systems in eccentric orbit. It's important that we understand these systems, since many of the post-AGB stars are in eccentric systems, and we also have the example of Taisas star that is very eccentric, so we also have eccentric AGB stars. So in eccentric orbits, the orbital separation will vary between maximum value at apastron passage, minimal value at periastron passage. This also induces that the orbital velocity of the stars varies within one orbital period. And this all complicates everything quite a lot, as you'll see. So here you see a first example of the morphology that we get in these eccentric systems. So at first you see that it's asymmetric. It's not this nice Archimedes spiral structure. And there's also some characteristic patterns appearing here that we see in eccentric systems. So at first there are low density gaps. So these are darker regions in between the higher density spirals. And then at the edges of these low density gaps, there are so-called bifurcations, which are locations where two spirals seem to split up or come together. And so we studied how these typical features actually arise in these eccentric models. And that is because of the phase dependency of the wind-companion interaction. So because we have this changing orbital velocity, changing orbital separation, you get this phase dependency. So to give an idea, you see here the wind structures that form close to the stars within one orbit, but at different orbital phases, so from left to right. And you see that this wind structure varies a lot, which is not the case if we have non-eccentric systems. So the stars are in periastron passage, so close together if the companion is at the left. After that, a bow-shock spiral structure forms because it interacts quite strongly with the wind. And then around apastron passage, this bow-shock actually travels away from the companion, and this is due to this change in orbital separation and change in orbital velocity. And then after that, a two-edged spiral structure starts to form. So within one orbit, we have these different wind structures around the companion. But if you want to see the details, I refer to my papers. Next to these quite typical eccentric systems, we also have some more complex morphologies that can appear. So here, for example, you see again that it's asymmetric, but we don't have these low density gaps or bifurcations. And this is the case when the wind velocity is lower. So then you get more complex things. So to give you an idea, I show you what is happening close to the stars. So here you see the wind structures that are forming. And you see that again, due to this phase dependency, the wind structures vary a lot during one orbital period. So yeah, this is all quite complex. But important is that it's still quite regular. Like you see that it's self-similar. So every orbital period, the same structures are forming, such that here you see these nice layers of each time the same structure. And also, you see that the companion has an accretion disk throughout the entire simulation. So then next to binary systems, we're also trying to understand what is happening in hierarchical triple systems. So we made some models there. So in our simulations, we have an AGB star with a close companion, and then there is an additional companion far away. And because of this additional companion, this inner binary will also orbit around this common center of mass, and it will again complicate everything. So yeah, we have a 1.6 solar mass AGB star with a 0.4 solar mass companion at 5 AU. And then we vary the orbital eccentricity of these outer orbits and the mass of the outer companion and the wind velocity of the AGB star. But this is still work in progress. But I'm going to already show you some things that you have an idea of what is happening. So this is, again, orbital plane view slice, and you see the density distribution. It's twice the same simulation, but more zoomed in on the right, so that you get a view of what is happening on both scales. So the inner binary, you see best on that simulation, is creating this quite compressed spiral that you saw before already, the Archimedes spiral, and then you have this additional companion that is also creating an additional spiral on top of this compressed spiral. This additional spiral is also affected by this inner spiral, such that the outer edge of the spiral is also quite wavy as it goes on the inner spiral. So then the global orbital plane morphology looks a bit like this. We can also increase the mass of this outer companion, so that is what you see on the new video there. And then you see better what the impact is of the orbital motion of the inner binary around the common center of mass. Because now this compressed inner spiral is also sort of orbiting around the center of mass, such that it's not just a normal Archimedes spiral, but it's more like a snail shell, because it's also orbiting around. But for a deeper analysis, you'll have to wait for my paper to be written. So that is what I wanted to tell you about the results of these hydrodynamic simulations. So then we come back to what the other people are doing in my team. So in the future, we would like to have a more physically complete wind model. And then we would also like to couple this wind model to chemical calculations. And that is what Silke Maas and her collaborators are working on. This is a difficult problem, as we have to solve ODE equations, but this has found to be computationally infeasible in 3 dimensions. It's just too complex there. So they are looking at a novel way to solve this problem, and that is by using a neural network. So what they want to do is that you have the physical state and abundances, chemical abundances, at the time step t. And then at the next time step in the simulation, you want to get the new abundances, but without having to do all these time-consuming calculations. And that is where the neural network comes in. So this neural network just wants to emulate these abundances, and you can train this network with the use of 1D models. So then our final goal is that we want to get a better understanding of these observations by using our simulations. So to couple this, we need radiative transfer. And we're not yet using MC-FOST, we're using MAGRITTE, which is a different code that is also doing a bit different things. So this code is developed by Frederik de Keuster and Thomas Koelmans, who are also at KU Leuven. MAGRITTE is an open source software, and it's also easy to use, so we can easily post-process it on our phantom models to get these observables. It's calculating the non-LTE line radiative transfer, and currently it is not yet model dust, so that's different than MC-FOST. It can be used on both grid-based models and SPH models, so you don't need a particular grid. And then MAGRITTE optimizes the grid by remeshing it in an optimal way to do the calculations smoothly. So then, to calculate the abundances using these radiative transfer calculations, it traces rays from a point in the remeshed grid, and then solves it. And this ray tracer is also the one that Mats Esseldeurs had already used and adapted to be used in our phantom calculations, but Lionel Sis will tell you more about this in his talk. So, to give you an idea of what we have done already with MAGRITTE, you see here just some ALMA observations of the star R Achille, so one of the atomium stars. So you see these 2D images, these are channel maps, so in each channel map you see all material of the CO line that is coming towards you or going away from you with a certain velocity. So if you put all these images next to each other, you get more of an idea what this 3D morphology would look like. And then with the use of MAGRITTE, we can also create similar things for our hydro simulations. So here you see one example of a triple model. But it's still really difficult to compare these things. So first of all, we want to have a more physically correct hydro model, because it's of course still a bit simplistic compared to what is happening in these very complex observations. But secondly, also because these observations are so complex, it's really difficult to know which simulations to make that will actually look like these observations. So that is why Frederik de Keuster and his collaborators are trying a different approach to this problem. So forward modeling is what we were doing, what I have just shown. So we want to make spectral line observations of our hydro models. But as I said, this is a difficult approach. So what they try to do is use the inverse method, where we want to make a deprojection of our observations. So make sort of models of our observations. So I showed you what we get from our observations that are 2D images. So if you want to make a 3D model, we have to go from these images where we have just coordinates in 2 dimensions and a deprojected velocity to go through a 3D model where we have these coordinates in 3 dimensions. So there's always some ambiguity, if we do that. So we also need uncertainty quantification there. But this is a project that is going on by Frederik to give us a new way to couple these observations with simulations. So I hope that now you have like a good overview of what all of us are doing and how we are working together to solve this problem of understanding these observations better by using the simulations also. So to conclude, what I want you to remember from this is that AGB outflows are very complex, and we think that the main cause of these complexities is the impact of one or multiple planetary or stellar companions that are still hidden in the wind. Our phantom models are already helping us a lot to understand how these companions can shape these winds, but it's still difficult to compare them to observations. But to do this, Lionel especially, is still working on the development of our models to make them more physically complete. And then we can use the radiative transfer solver MAGRITTE, or maybe MC-FOST in the future. And hopefully also the deep projection tool by Frederik to reach our goal of comparing this. And then one last thing, we still have an open postdoc vacancy in Leuven. Leuven is a really nice place to work. So if anyone is interested in doing anything with phantom or like computational things, you can always tell me or email Leen. Thank you for listening.
Just two quick questions. One is that you mentioned before when we were discussing you told me that the particles are generated from the point mass particle on the central star, basically, right?
Yeah, so it's on a sphere around the point mass.
Yeah. So in one of the on the slides you have the trinary system and you have 3 point mass particles, I assume.
Yes.
The 3 of them are generating winds? Or
No, only the AGB particle,
okay.
yes.
That was my first question. Second question was that since you're generating new particles, you are decreasing the amount of mass from the central one, or you keep everything constant that you generate?
No, wait. So it's not kept constant, so it can accrete material. I'm not sure. Yeah, I think it's also losing the mass.
Okay.
Yeah. Thanks. Yeah, they can vary.
I think that's correct.
Yeah. I'm not sure, but it can accrete at least. But maybe the Massless rate is, because it's also, for the time we have in the simulation, it won't matter. But
wouldn't be much, but I think you do keep track of it. It's a good question.
Yeah.
Thank you for the talk. So in your AGB binary simulations, what actually happens to the orbits?
Yeah, so that's an interesting point that we want to study also. And so I checked it out in my first simulation that I had, where we did not have the H1 cooling, and then it was interesting, but I didn't trust it that much because there were weird things happening, and then the mass transfer and accretion was like a bit weird. But now that we have these accretion disks, it's already better to trust it. But still, it's difficult because the time scales of these simulations are maybe not long enough. But different things happen sometimes in various simulations. So it's not like there's a real conclusion yet about that. But I'm probably going to look into that more. Yeah.
Any other questions?
Thank you. So there's already lots of things going on in the simulations, but like looking at the observations, it looks like the winds could be clumpy. So have you considered like doing clumpy winds?
I think that's still too difficult. I don't know. So we're really like building up the simulations by adding more and more things, and then in this way we also want to like understand the effect of anything that we include. So I don't think like really adding clumps itself is planned in the near future. But I think like if we already have dust included, and that will already change things, and if we have pulsations, that will also complicate things. So then we might get like a less nicely smooth wind already.
Yeah, I think the clumps would kind of change the opacity distribution, so it could have some interesting impact on it.
Rio and Jolien, why do you get clumps in the wind? What would cause that?
I don't know, but observations is clumps.
Yeah.
Do you have any idea why?
Like probably pulsations and irregular mass loss.
Thank you for the talk. I was wondering about the circumstellar disks that you show at some point.
Yeah, so
And how much mass can you get in there? My question is, would you think about forming planets in those second generation disks? Or is it impossible?
so it's not circumbinary, it's accretion disks, so only around one star always. I think the radius now is somewhere in between 0.5 and 1 AU. So I don't know, is that big enough to form planets? Yeah, it's pretty small. Yeah, no, they're pretty small. It's just like closely around the star. And was there another question? Okay. Do they grow? In the beginning, yes, but then they remain quite stable for the star. Yeah.
Another question. So, at the beginning of the talk, you mentioned that bipolarity in, for example, planetary nebulae, that's another feature that could be related to companion interactions in AGB binding. So have you looked into this? Do you think these interactions from a wide companion could lead to bipolarity?
Sorry, can you repeat the last part? So
in your simulations, do you think like interactions with companion could lead to bipolar morphology?
Not yet clearly. So the only thing we have is like we get this flattening a bit, and that could help already, but it's not enough yet, at least to get these bipolar outflows. In my first paper, I had some bipolar outflows, but that was due to the lack of cooling. So then we had that like around the companion, material was heating up so much that it got unstable, and then we actually had material escaping towards the poles, because those were the lowest density regions. So if you get material escaping, then it's around the poles at least, but in the models with cooling, we don't have anything like that yet. So
is that material collimated by like some kind of disk around the companion?
So if we had these outflows, we didn't have a disk, and now we have a disk but no outflows. So
it's sort of collimated by the winds.
Yeah, so it was material that is just being accumulated around the companion, but then material was too hot, so no disk could form, it couldn't settle, and instead it was blown away, and then it was in the edge, in the poles. But also the outflows were up to about like 40 kilometers per second, which is fast for our winds, but it's not compared to the bipolar outflows we see in post-AGB stars and planetary nebula. But yeah, it's a step towards maybe that it can happen there, but not anymore in our accretion disk case. So.
Right, thank you.